Let us discuss about the algebra of continuous functions. That is, whether sum of two continuous functions is continuous or not, or the product of continuous function is continuous or not, or the ratio of two continuous functions when the denominator is non-zero is continuous or not. So we shall discuss about the algebra of continuous functions. For this, to check or to determine the continuity of sum or product or the ratios of continuous functions, we use the definition of continuity of the function and also the algebra of limits of functions. So let us recall the definition of continuity of a function. A function fx is continuous at any point a in the domain if the limiting value of the function is equal to the value of the function at that point. In other words, we may write it as limit extending a of fx is equal to f of a. So we shall use this one, and also we note that limit of fx plus gx is equal to limit of fx plus limit of gx. So we use both these points, that is the definition of continuity and algebra of limits of functions, and we shall determine whether the continuity of sum of two function is continuous or the product of two continuous function is continuous, like that. So let fx and gx be two functions continuous at a point a in the domain. As usual, we note that limit extending a of fx is equal to f of a, and limit g of x as x tends to a is equal to g of a, because both fx and gx are continuous at the point a. Hence, we'll take the limit of fx plus gx as x tends to a, and by using the algebra of limits, we can rewrite it as limit of fx as x tends to a plus limit of gx as x tends to a. And by the above definition, we see that the first term is f of a and the second term is g of a in the sum. So we have limit extending a of fx plus gx is equal to f of a plus g of a. So this implies the sum of two functions fx plus gx is continuous at x is equal to a. The same argument can also be applied to the product of continuous functions, that is to determine whether fx into gx, where fx and gx both are continuous at x is equal to a, is continuous or not. So let us take limit of fx into gx as x tends to a. Again, this can be written as limit of fx as x tends to a into limit of gx as x tends to a, and again this is equals to f of a into g of a. In other words, limit of fx into gx as x tends to a is equal to f of a into g of a. So the product of two continuous functions is also continuous. You can also note that by using the same argument and algebra of limits, you can also see that if g of a is not equals to 0, in other words f of a divided by g of a is a finite value, then limit a extending a of fx by gx is equal to f of a divided by g of a. So we can state this as a result, that is, if f and g are continuous functions at c in the domain and k is any real number that is constant, then k times f plus g and f into g are continuous at that point c. Moreover, if g of c is not equals to 0, that is the denominator doesn't become 0, then a limit of fx divided by gx as x tends to c is also f of c divided by g of c. Then we can write it as f by g is also continuous at c. So we can consider some of the examples, very simple examples. Let us take sin x and cos x. Both sin x and cos x are continuous everywhere on the real line. For all values of x on the real line, both sin x and cos x are continuous. So let us take fx is equal to sin x and gx is equal to cos x. Let it be continuous at the point say x is equal to pi by 3. Then we note that the sum of two functions sin x plus cos x is also continuous at x is equal to pi by 3. The product sin x into cos x, in other words it can be also written as 1 by 2 times sin 2x, is also continuous at x is equal to pi by 3. Similarly, the product sin x divided by cos x, that is tan x, is also continuous at x is equal to pi by 3. Or if you take the reverse product cos x divided by sin x, both sin x and cos x are not equals to 0 at x is equal to pi by 3. So both the ratios exist. Tan x is also having finite value at x is equal to pi by 3 and cos x also has the finite value at x is equal to pi by 3. So you can note that the ratio either fx by gx you may take, that is tan x, or you may take gx by fx, that is cot x. Both are continuous at x is equal to pi by 3. So similarly you can consider cosec x or secant x. Both are continuous at x is equal to pi by 3. Now we shall discuss about the algebra of differentiable functions. Of course, you may note that for a function to be differentiable at a point, it must be continuous. That is, the continuity is the necessary condition for the differentiability of the function, but it is not a sufficient condition, because even though function is continuous, it may not be differentiable. Already we have discussed about it. For example, mod x is continuous at x is equal to 0 but not differentiable at x is equal to 0. So you may note that continuity is the necessary condition for the differentiability of a function but not sufficient condition. In other words, we can say that differentiability implies continuity of a function at that point, but the converse is not true. Now we shall concentrate on the algebra of differentiable functions. So we shall take let ux and vx be two differentiable functions at a point say a. Then the derivative of c times ux, where c is a constant, and the product of functions ux and vx, sum of the functions ux and vx, the difference of functions ux minus vx, and the ratios ux by vx are also differentiable at that point a, provided the denominator is defined. In other words, we can say that if two functions ux and vx are differentiable at a point p, then their sum ux plus vx, their difference ux minus vx, and a constant times ux, constant times that function, and the product and the ratio of functions are all differentiable at that point p. For the proof, we shall first prove that the sum of two functions, that is ux plus vx, is differentiable when both ux and vx are differentiable at a point a. So let us take let us take y is equal to u plus v be the sum of two differentiable functions. Let delta y, delta x, delta u and delta v be the respective small changes in y, x, u and v. Then as we have taken y is equal to u plus v, the respective change in y, that is y plus delta y, can be written as y plus delta y is equal to u plus delta u plus v plus delta v. Now divide the entire equation by delta x. So it becomes delta y by delta x is equal to delta u by delta x plus delta v by delta x. And as delta x tends to 0, you can find out this one. So we can write dy by dx is equal to du by dx plus dv by dx. In other words, d by dx of u plus v is equal to du by dx plus dv by dx. Similarly, we can write d by dx of u minus v is equal to du by dx minus dv by dx. Now we apply the same argument for the product of two functions. That is, let us take y is equal to u into v. Y is equal to u into v. Then a small change in y, that is y plus delta y, can be written as u plus delta u into v plus delta v. Now we can rewrite it as by using algebraic laws. That is, the product is distributive over addition. That is, we write it as u into v plus v into delta u plus u into delta v plus delta u into delta v. So subtracting y on both sides, that is, delta y can be written as delta y is equal to u into delta v plus v into delta u plus delta u into delta v. Again, you note that y is equal to u into v, so both the terms y and uv and LHS and RHS get cancelled, so we retain the expression. Again, by dividing by delta x, and then delta x tending to 0 will take, so this LHS will become dy by dx. This is equals to limit delta x tending to 0 u into delta v by delta x plus v into delta u by delta x plus delta v into delta u by delta x. So as delta x tends to 0, both delta u and delta v also tends to 0. So the last term in the sum, that is delta u into delta v by delta x, goes to 0. So taking the limits on other side, we have, it is u into dv by dx plus v into du by dx. So we can write d by dx of u is equal to u into dv by dx plus v into du by dx. So when you take y is equal to c into u, where c is a constant term, you may let u is equal to c and again apply the above rule, and you can find out d by dx of c is equal to c into du by dx. So this completes.